Hello, I welcome you all to this another interesting screencast. The problem reads, the linkage is subjected to a force of P equal to 6 kilonewtons. Determine the angle theta for equilibrium. The spring is unstretched at theta equal to 60 degrees. Neglect the mass of the links. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. In this particular problem, we're going to use the virtual work method. This method is an alternative to the equilibrium of a particle method. It is also an alternative to the equilibrium of rigid bodies. It is also an alternative to the equilibrium of interconnected rigid bodies. So therefore it means you are able to use all the other methods, which are the equilibrium of rigid bodies or interconnected rigid bodies, to still solve for the angle which will ensure that this particular structure is in equilibrium. Alright. So what is virtual work method? Virtual work method states that the total virtual work in a system is equal to 0. So del U is equal to 0, and this is equal to the summation of work being done by the force, This is both active and reactive forces times the translational virtual displacement. So this is virtual work due to the forces. You can also have virtual work due to moments or couple moments as a product of moment and rotational virtual displacement del theta. So the total or the net virtual work in a system is equal to 0. So given a force and translational virtual displacement, they are supposed to be collinear. That's one condition for the work itself to be there. And if they are in the same direction, you have positive virtual work. Otherwise, you have negative. The same applies to a couple moment. They are supposed to be collinear or parallel. And when this happens, then you have positive virtual work. Otherwise, you have negative. So basically, this is the method for virtual work method. And all the problems that we are going to be dealing with are single degree of freedom problems. And by this we mean we are able to locate any point within the system, be it a force, by just using a single coordinate, which is theta. Right. So let's start solving this particular problem. The first step is always drawing the free body diagram. After drawing the free body diagram, we need to draw another free body diagram for the deflected or displaced configuration of the same system. Okay. So at the hinge A, we expect to have a reaction force like so, and then we'll have another reaction force like so. And then at this point, we are going to have a normal force like so, which is a reaction force. Alright, let's label these ones. So let's call this one CY, we call this one AY, and then we call this one AX. Alright, once we've done this, then we need to apply a virtual displacement. This can either be translational or rotational. So we are able to apply that at point A, at point B, or point C. It's really up to you. The solution still remains the same. For me, I'm going to apply a virtual translational displacement at point C. Okay, so I'll apply a virtual displacement in this direction like this. Alright. So this is my vector displacement at this point like this. All right, so let me call this particular vector displacement, this one here, as my del xc. Okay, so let's draw the configuration of a deflected or displaced system. So we'll have a system like something like this. Okay, all right, something like that. It may not be that very perfect. So we expect to have some we're going to expect some movements at B in this direction like this, as well as in this direction like this. I'll put it on top like so. Okay, so this movement, let's label this. So this one here is going to be equal to, this movement here is going to be equal to del x b, and then this one will be del this one is del y b. All right, of course we do have some rotations taking place there and so on, but we don't have any couple moment and so on. Okay, therefore we are not going to have any vector work at point A. So once we've done this, we now need to write down the vector displacement equations. So I think the free body diagram is not yet done. We'll cut the spring at this point, and once we cut the spring at that point, we expect a spring force like so. Okay, so we're going to expect a spring force like so. All right, like so. Great. So let's call this force here is Fs. We call this force here Fs. Okay, so this is the spring force once we cut the spring there. All right. Our reference fixed point that we've picked is A. So the points that we expect to have vector work is point B in the horizontal direction, where else, and point C also in the horizontal directions. Okay, so we have two horizontal, right? One due to the spring force, the other one due to the force P. The masses of the links have been neglected. So these are the only points that we are going to define. So let's do the definition right away. So we're going to have something like so there to there like this. We'll define this point. And then we'll have another point from here to there. We'll also define this point. Great. So there we go. There we go. Great. So what we need to do now is label this. So this we are going to call it as XB, and this one we'll call it as XC. All right. So let's now define them. Before we define this, let's define our the spring force Fs. This is equal to the spring constant K times the stretch, and we have K already given, and K is equal to 20 kilonewtons per meter, and S is equal to L final minus L naught, and L naught is already given to us. We've been told that the spring is unstretched at theta equal to 60 degrees. So we have got two lengths there. So we say 2 by the length of which one is 0.9, and then cos theta. Okay. All right. So we know cos theta, therefore L naught is just going to be equal to 2 by that is 0 point, this is a 1.8 cos, because we know theta here, theta we've been told is 60 degrees, right? So at 60 degrees, and 60 degrees we know is 0.5, so this gives us 0.9, right? 0.9 meters. So that is the original length, right? Okay, so we have that, and then L final is just going to be equal to of course both of them is just 1.8, the stretched one 1.8 cos theta. We don't know what that stretch is. Okay, great. Therefore our Fs is just going to be equal to 20 by 1.8 cos theta minus 0.9. Okay, and if we are to write this, we have a 20 by 1.8. This gives us a 36 cos theta minus that's 20 by 0.9, that's 18. Okay, so that is the value of our Fs. Okay, so now let's define these equations. So we have xb is equal to xb is equal to 0.9 cos theta. Okay, right? And therefore finding the vector displacement del xb is going to be equal to minus 0.9 sine theta del theta. Of course we want an absolute value, so this is just going to be equal to 0.9 sine theta del theta. Then we have another value which is xc is equal to this one is just like the length is equal to 1.8 0.9 by 2 then cos theta. Therefore the derivative or the partial or the vector displacement is del xc, which is just equal to a minus 1.8 sine theta del theta, and taking the modulus so that we have the absolute value. This just gives us a 1.8 sine theta del theta. Alright, Let's now plug this into our equation, which is del u equal to 0. Of course, at point A, no virtual work. At point B, we'll have virtual work in the horizontal direction. At point C, we'll have virtual work also in the horizontal direction. Alright, at B, both the virtual displacement and the force are in the same direction, therefore we expect a positive virtual work, so we'll have a P del xb. Okay, and then at C, we have a virtual displacement in the opposite direction of the spring force, so we'll have a minus Fs del xc equal to 0. So let's replace this value. So we have a P del xb. We calculated del xb is 0.9 sine theta. Okay, del sine theta like that, minus Fs. We calculated Fs already. We said it's a 36 cos theta minus 18, like so, bracket it, and then we have del xc is 1.8 sine theta del theta, like that. All right. Okay, so here we expect del theta, we factor out del theta, so this will be 0.9 p sine theta minus multiply 36 by 1.8. This gives us a 64.8 cos theta sine theta. Then we have a plus 18 by 1.8. So this gives us a 32.4 sine theta equal to 0. Del theta will not be equal to 0. So the only part that will be equal to 0 is this part here. Okay. So let's work on that part. Of course, we can factor out sine and it goes. And then we can write this equation as follows. Let me just get some space here. We can write that equation as follows. I get some space inside here. Right. So this is just going to be equal to, this will be equal to cos theta is equal to 0.9 p plus 32.4 divided by 64, divided by 64.8, and we know that P is equal to 6 kilonewtons. Therefore, theta is just going to be equal to, plug in P there, so 0.9 by 6 plus 32.4 divided by 64.8, and cos inverse of that, we have a 54.31 degrees. So 0.9 by 6 plus 32.4 divided by 64.8, cos inverse of that, 54.31. Alright, So this is the value of theta that will ensure that the system of interconnected rigid body remains in equilibrium. I hope this video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.